Our last little video here for the magnetism unit is on reactance and signal filters. And so this is an investigation of how you might use an RC filter or an RL filter to do some interesting things in a circuit. So we'll start with the idea of reactance. Because they take time to react to changes in a current, capacitors and inductors behave differently when we put them in AC circuits, right? So if we put a capacitor in a DC circuit, we watch it charge and then it's charged, okay? Same with an inductor. It takes a little minute before the current can run freely through an inductor, but once it does, it acts just like a wire. And so we don't need to worry too much about an inductor or a capacitor after the current is up and going. But in an AC circuit, that voltage is moving back and forth all the time. So the current is changing directions through that inductor or a capacitor. And that means that it's constantly being affected by the characteristics of that inductor or that capacitor. So let's think about an inductor. When we turn on the voltage here, say our current starts going in this clockwise direction, right? What does that inductor do? It resists that change in current, right? So it's going to create a voltage pointing upward here to try to block that clockwise current, right? Well, as soon as that voltage switches in the other direction and starts to make a current in this direction, that inductor is going to resist that change of current by trying to create a counter current that goes in the downward direction. So that's what that inductor is going to be constantly fighting the changes in the current. And we can see that here in this plot. And this, I don't want to get too much in the weeds here, but it's really kind of interesting. What you get is a phase difference between the voltage and the current, right? The voltage, say down here from A to B, the voltage is trying to make the current go in the negative direction down here. But that inductor is resisting that, and so the current continues to go in the positive direction. It's getting smaller, the voltage is making the current smaller, but it's not able to immediately get it to go in the negative direction because that inductor is resisting the change. And so that phase change here that you see is typical of an inductor AC circuit. The current, we might think of it as trying to catch up at all times with what's happening with the voltage. What that means is that the more frequently that that signal changes, the more frequently our signal goes from positive to negative, the more resistance that inductor is going to offer. And that kind of resistance is called reactance. It's inductive reactance. We can just think of this as a kind of resistance, but it's a resistance that is a function of the frequency of the signal. Okay, so normally we'd say, oh, my resistance here is 20 ohms. Okay, but in this case, the resistance, or more properly, the reactance, is a function of the frequency, right? It has to do with what the size of my inductor is, right? But it also has to do with the signal that's moving through it. So if I have a really fast signal with a high frequency, I'm not going to have a very big current, okay? Because it's going to be, the voltage is going to be moving back and forth very quickly. The inductor is going to be constantly resisting that. And so I'm going to have a high reactance. And that means my current through the circuit is going to be really slow. If I have a slower AC voltage, a slower AC signal, then my reactance is going to be lower and the signal is going to make it through with very little resistance from that inductor. The result of that is what is called a filter. Okay, if I have for instance, take this little green signal. Sometimes when I'm collecting data, say, I might have a low frequency signal, this blue line, that I want to get from my data. And I've got a bunch of, say, noise in my system that's giving me this high frequency oscillation within my low frequency signal. I want to get rid of that up and down, right? Because I just want to see that blue line. That's the data that I want. I would use a low pass filter. I would set up an inductor circuit like this, and it would catch that high frequency part of the signal, the quick up and downs, and it would eliminate those, right? It would get rid of those high frequency oscillations, and I'd be left with just this low frequency signal. That's called a low pass filter because it allows my low frequency signal to pass through and it filters out my high frequency signal. A capacitor does just the opposite, and it has what's called capacitive reactance, right? Because in a low frequency signal, what happens? Well, I get initially a big current, right, um, as the electrons move through the wire to charge the capacitor. But then once this is charged, there's no current anymore. Okay, so in order to keep a current going, I have to have a really fast oscillation so that the capacitor doesn't get fully charged and essentially break my circuit, stop the current. So the faster I have a frequency in this case, the lower my reactance. If I have a really low frequency, I'm going to have a high reactance or a high resistance in that circuit. The result there is I have that same green signal here. I'm going to get rid of that low frequency signal, and my filtered signal is going to be this orange high oscillation signal. Okay, so this is called a high pass filter because it allows my high frequencies to go through but pulls out my low frequencies. And so that's a result of capacitive reactance. So that's just a little hint at what the kind of interesting things you can do with inductors and capacitors when you have an AC circuit. AC circuits tend to get more complicated because of the way that the circuit components like capacitors and inductors react in time.